All right, now to get down a little bit more to the nitty-gritty. For those of you interested in or already working on, better yet, the Integrated Functional and Safety Specifications project, which is the most challenging project and also the project that I, the crazy Ethan Whitmore, and the lovely Kelly Tran all got to work on together last year. They were awesome coworkers, colleagues, friends, by the way. If you see them on campus, tell them I said so. But what I want to do with that is give you guys a basic overview, kind of a high-level, intuitive, simplistic description of what that project was all about. All right, so if you're familiar with safety software at all, you know that there are certain fields that focus on safety more than others. Some of the big ones are the medical field, medical equipment, nuclear anything, nuclear power, nuclear weapons, that kind of thing, which brings me to the other one. Military is important, and military weaponry, planes, that kind of thing. And finally, automotive, cars, making sure your brakes work, airbags go off. There are a lot of safety issues to be concerned about in all of those fields. And common to every single one, you've got a group of people that is trying to make the device work. They're working on the function. They're trying to make sure it will do what it's supposed to do in the first place. With an X-ray machine, for example, you want to make sure that that X-ray machine, when the operator presses the button to do an X-ray, it actually does an X-ray according to her specifications. Now, that's pretty simple. Yeah, you want to make it happen, but it's the functional team's job to design the system so that it accomplishes the task, both physically and in software. You want to design it to do X-rays. On the safety side, you want to make sure things don't happen that aren't supposed to happen. With X-rays in particular, and this happened in the 80s, by the way, it was actually with radio treatment for cancer. People got overdoses and wound up dying, several of them, probably because of those overdoses. And it's the safety team's job to see, okay, we've got this X-ray machine. It is a dangerous device. It could kill people with overdoses, or if it goes off at the wrong time, maybe they don't have the protection, maybe it goes off and burns out someone's eye. There are so many ways that it could go wrong, and the safety team's job is to figure out how they can make sure that the undesired situations do not occur. They figure out every possible way it can occur, and they try to make modifications to the system to make sure that such problems don't occur. Now, the way this happens in the field most of the time, and in all of these areas, is you got the functional people doing their thing, and you got the safety people doing their thing, and they don't really communicate all that much. They have completely separate ways of thinking. These guys are creating and making things happen, whereas these guys are stopping things from happening. They're not trying to stop the functions from happening. They're trying to stop other things, but it's a completely different way of thinking about things. So you've got separate guys, separate people, separate groups working on the same project, but thinking in completely separate ways, and yet their sides are absolutely connected. And that's where IFSS comes into play. If the system is designed correctly, then we can make sure that we can design the system such that all of these problems that might happen over in the safety side won't occur. But in order to do that, you've got to get communication going on between the functional people and the safety people. And that's okay at a high level when you're dealing with something more qualitative, but because we're working in software, this is more rigid. This is more formal, fixed, and mathematical. If you're not familiar with software testing, now certainly you could do software testing like a lot of beta testers do with games where you just kind of play through it and say how you feel about the interface, whether it seems like it gets done what you want it to do. But when you're dealing with stuff like this, that's not how any testing goes, any software testing. Software testing says, this is the input that I give, these are the parameters I set, this is the output I want, and this is the only output I want. And, I mean, when you're dealing with the game, it's okay if the game crashes. I mean, we really don't like it, but it's okay if the game crashes. When you're dealing with a nuclear power plant, it's not okay if that thing crashes. Things like Chernobyl, if you're not familiar with it, it's a nuclear meltdown site in Russia. I don't think it was a result of a software failure, but it's what happens when nuclear reactors melt down. So the possibility of software causing that, we want to prevent. And actually, just yesterday, Iran had another virus hit their nuclear centrifuges, and it screwed everything up. It's the second time it's happened to them, which says that software is a fundamental part of that system. It's not like they've got a bunch of safeguards in place. They may, but software has a huge hand in it, and software is the reason that they've had such setbacks. So take this seriously. Software is very intimately involved in each and every one of these situations, whether it's making sure your airbags go off. I mean, that's probably controlled in a computer chip in your car nowadays, or making sure you don't get an overdose on that x-ray machine. Most of that, at some point, I think during the 80s, according to Nancy Levison's Safeware, they started moving away from the hardware locks, safety locks that would prevent overdoses from happening. They just figured, well, the software can do it. If the software doesn't do it, nothing will do it. So there's the capability of giving people overdoses. If the software that knows it's supposed to detonate that rocket malfunctions, then it could blow up your airplane and your pilot. Or it could blow up 1,000 civilians you weren't aiming at. All of those are possibilities that you want to avoid when you're dealing with safety. And again, getting back to the software side of this, we've already established with all of these products, you've got your functional people, you've got your safety people. But when you deal with software on these kinds of systems, you're not dealing with human interaction so much. I mean, you do deal with human interaction, but you want to make sure that regardless of any human input, oftentimes it's just to assume that humans are stupid, because that's what causes safety problems. I mean, it's better said they're unreliable, but we're not concerned with the humans. We're concerned with the software. We want the rigid side of everything. We want to know every discrete way. We want to break the situation down. The safety team over here is working with fault trees. They figure out systematically every possible combination of events that can come together in any imaginable way that they can think of that could cause that one problematic event to happen. Then they figure out every way it could happen. They may have several different top-level events that they don't want to see happen, and their objective is to stop it. They figure out every way it can happen, and they want to prevent it. And again, a fault tree is discrete. It's not qualitative. It's not, we'll do this measure to prevent it and this measure to prevent it. A fault tree figures out in a mathematically accurate and perfect way how things can happen. Now, fault trees may not be completely accurate and comprehensive, but they're formal in the mathematical sense. And over here, when you're dealing with software, well, it's already formal. I mean, you're programming something. It has formal specifications about how it works. That's what software is. So you take this formal model and this formal model and you plug them together, and this is where it gets a little bit fuzzy, but it makes sense. These guys are breaking it down into individual components that can break, and all those individual components come together to cause the big problem. These guys, on the other hand, are thinking about what individual components to make, how to design them, how to use them. And if you can connect all of those together and get the two formal systems together, then you can run the formal tests. I was mentioning earlier that with software, we don't normally do, at least with this situation, we're not thinking about informal tests where people go through and click through or type test certain things. We want to create automatic tests that go through this entire model and test every possible situation to make sure that any given combination of events that occurs in our functional specification won't come together to cause the issues that we've described, the problems that we've described in our fault tree. So that's the basic idea of IFSS. And I hope I've been small enough, intuitive enough for you guys to understand. If you have any questions, always feel free to either comment on the video or email me. Dr. Wong has my email address, and I will do my best to help you guys out. But I will follow up with where we are in the research process, and we'll go from there.